Okay, good afternoon, everybody. Just check in. Can everybody hear me?
Yes, sir.
All right.
Yes, sir.
All right. And who's the last person? I'm seeing one more person. All right. I'm hoping that person could hear me as well. All right. So this session 8, will complete the syllabus requirements that um, you are required to cover. All right. So we'll be doing a tutorial based on those requirements. You would have gotten it in the course that I had put up for you, but again, I'm running over the main points, right, in these tutorials. I hope you all have been working on the multiple choice, and I put up some paper 3-2s for those who have to do it. We have the questions and the solutions. I just sent one on the chat. All right. So let's see what we have here. All right. So we are looking at transformations first, and we have had covered already translations, right? And there was a main equation that we use for all translations, and it was start point plus translation vector equal to end point, which I have up on the left-hand side corner. So we had done work on that in the last session, session 7, and even before that. Now, from now on, from today, all the other transformations that we will look at, right, they will have this second type of equation, which is transformation matrix, right, multiply by object matrix will always give us the image matrix, all right? And this equation is what will help us to solve any equation or any question that is dealing with the other transformations that we need to know about, right? Now, in the majority of them, they give us the object points, from which we will make the object matrix. They will give us information, right, whereby we will either have the transformation matrix, or based on our teaching today, we will know how to come up with the transformation matrix. So in the vast majority of questions, you'll just have to multiply these two and you'll get your answer here. All right. Sometimes they give you the image matrix and they give you, for example, the object matrix, and you have to find the transformation matrix, right? That was shown in your course that I gave you. That comes very infrequently, right? And that's mainly a paper 2 question. And then the final one is they give you the transformation matrix, they give you the image matrix, and you tell you find the object matrix, all right? And you can also get that done utilizing this equation. So, but the main one that we're going to be using over and over again is what we're covering in today's tutorial. That is to say, they want to find the image, and we are given the object points, and we have to find the image points. So we're going to form an object matrix multiplied by a transformation matrix, and we'll get the image matrix. Okay, so let's see how that is done. So we're going to look at reflections, right? That's what we're going to look at to start, reflections. So the first type of reflection we're going to look at is a reflection in the x-axis. And I am going to ask you to memorize some key words, right, that will help you to do these type of questions, right? The key words you would have encountered already, so this is more or less a reminder. And for reflection in the x-axis, what are the key words? They would be keep the x, right, change the y. That's what I'm highlighting here, right? Keep the x, change the y. Okay, so what do I mean by that? All right, well, if we look here, right, if I had to do a reflection of this object in the x-axis, right, I could do it by drawing or I could do it by calculation. In order to do it by calculation, I need to utilize this equation that we just learned up here. transformation matrix times object matrix equal to image matrix. So I need to know what the transformation matrix is, which is what I have here. I need to know what is the transformation matrix for reflection in the x-axis. Now, some people would memorize it. I have no problem with that. You could go ahead and memorize it. But it's very useful to learn these words, which is keep the x, change the y. Very, very useful. Because if we were given the points for A, B, C, and D, right, either through drawing, like they give you a drawing like this, or they give you it in the question, right, we could easily work out what A prime, B prime, C prime, and D prime is by knowing these words. Keep the x, change the y. So let's suppose they give us A as 2, 1, right, B as 3, 3, C as 6, 3, and D as 5, 1, right? For a reflection in the x-axis, which is written, reflections are use the symbol M. M meaning mirror line, being the OX line or the x-axis. So this really means a reflection in the x-axis. Once we learn, keep the x, change y, what that means is a point xy becomes x because we keep in the x, and then minus y because we change in the y. Changing the y means change it to the opposite sign. That's what change the y means, change it to the opposite sign. So whatever, if it was positive, it would become negative, and if it was negative, it would become positive. In other words, you just change your sign. So without doing any calculation at all, we know the answers up front. It's kind of like a little, a little advantage, a little ratch kind of smart move that a lot of people don't know. So those people who simply memorize this, they wouldn't know what I'm telling you here now. Just keep the exchange UI system. So I could write the answers right away without doing any calculation across here. I could keep all my x values, which are 2, 3, 6, and 5. You'd see it here, 2, 3, 6, and 5 for the answers for A prime, B prime, C prime, and D prime. And to get the y values, I would change the y sign. So if this is 1, for the image A prime, it'd be minus 1. If in B, the y value is 3, for the image, which is B prime, the y value will be minus 3. Here, C in the object, right? 3 is the y value. On this side, it'll be minus 3 for C prime. And then the y value here for D is 1. For D prime, it'll be, you change this number, but change the sign. So it'll be minus 1. So right away, without any calculation, I could actually know all the answers, right? But I can't just write it down like this because they will know that, we utilizing something else. So what we have to do in the requirement for CSEC is we have to use this equation here and come up with the transformation matrix for reflection in the x-axis. But how do we come up with this transformation matrix? Well, it's very easy. Well, either you memorize it or you use this system here. You're going to see what happens to 1, 0 under our rule. What rule am I talking about? Keep the x, change the y. And then that will give us this first column here of the transformation matrix. Then we're going to see what happens to 0, 1 under the same rule, which is keep the x, change y. And that will give us the second column of this transformation matrix here that they want us to either memorize or find in some way. Okay, so to get these here, this rule is going to apply, which means I'm going to keep the x, which is the 1, I'm going to keep it, change the y, the 0. But if I change 0 to minus 0, doesn't matter. So it's still written down as 0. So under the rule, what happens to 1, 0 will give us this column. And let's see what happens to 0, 1. I'm going to keep the x, so I'm going to keep the 0. And I'm going to change the y, because the rule I'm talking about is this one that you memorize before you go into the exam, right? And I'm going to change this 1 to minus 1. So what I have in fact done there is to find my transformation matrix that I'm going to be using, right, in this equation. This 1, 0, 0 minus 1 is this here, 1, 0, 0 minus 1. All right, so that's how we go about finding the transformation matrix if we didn't memorize it. But for me, I like to cover all bases. I'll memorize it and I'll know the way to come up with it in case, I'm a little flustered or I forget for some reason. I could always work it out. All right. So that's how we come up with this here. So that's the transformation matrix. Now we have to multiply that by the object matrix. What is the object matrix? The object matrix would be the matrix made up by all of the object points written vertically. So this here would be A, 2, 1, right? That's this A, 2, 1. So we write it down. Then this one here will be B, right? Look, B is 3, 3. So we write it vertically, 3, 3. This one here will be C. So C is 6, 3. So we write down 6, 3. This one here will be D. So you look here, D is 5, 1. Write down 5, 1. Now, if you did not memorize, keep the exchange UI, and you only learned this by memory and you walk in there, okay, I know the transformation matrix, you would now have to multiply this out, right? Multiply it out using normal matrix multiplication, which is 1 by 2 plus 0 by 1, right? That will give us this one here. Then row by column again will give us this answer here. So it'll be 0 by 2 is 2. Minus 1 by 1 is minus 1. 2 minus 1 is 1. Sorry, that isn't correct. 0 by 2 is 0, sorry. And then minus 1 by 1 is minus 1. So 0 minus 1 will give me minus 1 here. So let's do it for this one. So you'll see if you had to multiply it, what you do again, right? It'll be this row by this column will give me this one at the top. And then this row here by this column will give me the one at the bottom here. So let's do the first one. Let's get this answer here, right? So row by column. So it'll be 1 by 3 is 3. 0 by 3 is 0. So 3 and 0 will give us 3, which is this here. Then we're going to multiply this row now by this column again, as I said, to get this answer. Let's do that. 0 by 3 is 0. Minus 1 by 3 is minus 3. 0 plus minus 3 or 0 minus 3 is minus 3, which is this answer here. And that is the process you would need to go through if you had only memorized this, right? But because you are getting instructions from me, and you go into the exam knowing this, for reflection in the x-axis, we keep the exchange UI, we could write down all of these answers without doing the calculation of multiplication, and they would never know, because you are expected to be able to do this in, just pure mental without writing down anything. So how could we write down this? Well, we keep in all the x values. This is what it says, keep in all the x values. So 2, 3, 6, and 5 are all kept. And we change in all the y values. So if it's 1, it becomes minus 1. 3 becomes minus 3. 3 becomes minus 3. 1 becomes minus 1, because we're changing all the y signs. All right? And then the final step would be to take these and write them down horizontally. So like this one would represent A prime. This is B prime, C prime, and D prime. So let me write it in so you will just quickly see what I'm talking about here. Right? So this here was A, B, C, and D. And this one be A prime, B prime, C prime, and D prime. Okay, so that's how we would have gotten this. But remember, we do not, if they're asking for coordinates, for example, of the image points, then we cannot write it vertically like this. We cannot leave our answer like this. We have to put it in this form here. So A prime would have to be written horizontally. So this 2 minus 1 has to be written like this, horizontally, 2 minus 1. B prime, 3 minus 3, that has to be written horizontally like this. C prime, 6 minus 3, horizontally. D prime, 5 minus 1, horizontally. So you would write your final answers in this format here. Good? But in your exam, you cannot just write this goes like this. They don't want that. They want you to use a transformation matrix, multiply it by an object matrix, and get your image matrix. But this here is a little advantage I'm giving you here, that you'll be able to actually work out the answers without doing the actual multiplication. All you'll do is simulate as if you're doing the multiplication, okay? All right, so that's reflection in the x-axis. You're also required to know reflection in the y-axis. So if reflection in the x-axis was keep the x, change y, then reflection in the y-axis would be keep the y, change the x. So let's put that in. Let's write in or highlight keep the y, change the x. All right, that's what you're supposed to memorize for the second situation, which is reflection in the y-axis. Now, before I go to doing the calculation here, let's just quickly jump back here, come back up, and look at if we had to do not a calculation, but a drawing. In other words, if they had given us the object points or draw the object first, how we would have gotten the image. Well, that's quite easy. What you do is you check the perpendicular distance between the mirror line, which is the x-axis, and the points. So the distance between this mirror line here, which is the x-axis or the OX line, and A is this distance from here to here, which is 1 unit perpendicularly. So what we do on the other side of the mirror line, we measure that same distance. So if it's 1 unit up here, we'd have to measure 1 unit down to get the image of A, which is A prime. If B is 1, 2, 3 units up, to get the image of B, which is B prime, you'd have to go down in the opposite direction, which is down 3 units. 1, 2, 3. So that's how we get B prime. D is 1 unit up, so D prime would be 1 unit down. And C would be 1, 2, 3 units up vertically, perpendicularly up. So C prime will be 3 units down vertically, perpendicularly down. Remember, it's always perpendicular distances from the line. So 1, 2, 3 would give us C prime. All right. So that's how you do the reflection utilizing the drawing method. Let's come back down now to reflection in the y-axis, where we're going to keep the y and change the x. So again, our equation will be transformation matrix times object matrix will always give us the image matrix. This will always be the equation for every transformation besides translations, right? Translations is start point plus translation vector equal to end point, which is what we had done before. All the other transformations, we must apply this. So to get the transformation matrix for reflection on the y-axis, just like we did up here where we saw what happened to 1, 0 under our rule and 0, 1 under our rule, giving us these two columns of the transformation matrix, we have to do the same thing to get the transformation matrix for reflection in the y-axis. So what we do is we take 1, 0 and we apply the rule. What is the rule? The rule is for 1, 0 and all of them is keep the y, change the x. So if this is the x and this is the y, we're going to keep the y, which means we're going to keep this and change the x to the opposite. What's the opposite of 1? It's -1. So that's how you get -1 here. And that's going to be our first column in our transformation matrix. How do we get this column here? Well, you get this column by seeing what happens to 0, 1. See, we did 0, 1 here, give us this column. 0, 1 is going to give us this column here as well in this transformation matrix. So what are we going to do? Keep the y, change the x. So this is x and this is y. We're going to keep the y. So notice the y here is kept and change the x. But of course, if you change 0 to -0, no effect. So there you go. It still remains as 0. So this here is our transformation matrix. We're multiplying it by our object matrix. Where do we get the object matrix from? Well, we write down A, B, and C, right? A, B, and C, if we get it from here, or we get it from the question, it was these. This is A, this is B, and this is C. So let me write that in for you so you'll remember that. So this is A, this is B, and this is C. Right? So if we had these, or you had to read it off from here, and they wanted you to calculate the answer, because sometimes they tell you to calculate, then you would have the transformation matrix using our system here, or if you memorize it, and you would have to multiply this out. If you know our system, then all you have to do to get the answers is keep the y, change the x. So all these y values here, we're going to keep them. So 3 is kept, 0 is kept, -2 is kept, and we're going to change the x. So if this is -4, it becomes +4 here. -1 becomes +1 here. -3 becomes +3 here. And so our image values, image, A prime will be 4, 3, B prime will be 1, 0, and C prime will be 3, -2. So again, if they are asking us to calculate the coordinates of the image points, which would be A prime, B prime, and C prime, we would have had to write it horizontally. We cannot leave it in this form. This is just the calculation process. So what we do is to take 4, 3 and write it horizontally. That'll be A prime. B prime 1, 0 will be written like this. C prime 3 minus 2 will also be written horizontally. Okay? So don't forget, that is the method that we will be using. Let's go to the next one, which will be reflection in the line y equal to x. So far you learned reflection in the x-axis, reflection in the y-axis, and now you're looking at reflection in the line y equal to x. So in reflection in the line y equal to x, right, we interchange x and y. That's our rule that we have to learn, right? Our special rule that we learn to give us an advantage in the exam. What is the rule? Interchange x and y. So to get our transformation matrix, to get this column here, the rule R we're going to apply to 1, 0 is interchange. So 1, which was x, will interchange with 0. So you're going to get 0, 1, and that's how you get 0, 1 here. To get this column, we apply our rule now to 0, 1, right? Just as we did in the 2 previous examples. What is our rule? Interchange x and y. So 0, 1 will become 1, 0, right? 1, 0. So this here is our transformation matrix that we must use in our formula. So to get our answer, we would take the transformation matrix 0, 1, 1, 0, 0, 1, 1, 0, and multiply it by A, B, C, D. So if we look at A, B, C, D here, you would get A, B, C, D values from here, or if they give it to us, you write it down A, B, C, D, and we simply multiply this out. But remember, if you multiply this out, right, you will be taking a longer path. All you have to do to write down your answers would be, you could put an equal sign. Sorry, let me take off that. You just simply put an equal sign, and we could write down what A prime will be, B prime, C prime, and D prime. How come? Well, our rule, interchange x and y, so we don't have to actually do the calculation. We just use our rule. So this number here, 3, 2, we interchange, so it becomes 2, 3, right? 5, 2 will become 2, 5. 5 minus 1 will become minus 1, 5. And this one minus, let's minimize it a bit. Oh, it's right there. I didn't see that. And 1 minus 1, right, will become minus 1, 1, which is what we have written down here. 2, 3, 2, 5, minus 1, 5, and minus 1, 1. Of course, in the final answer, we wouldn't leave it in this form. We would write it horizontally. For example, A would be written as 2, 3, right? B would be written as 2, 5. C will be written as minus 1, 5. And D will be written as minus 1, 1, right? So you don't ever leave it like this, as I said before. Good? But again, I did not show you how to do up here, how to do the drawing. So let's come back up here for reflection on the y-axis. This is the mirror line, is the OY axis, right? So if you're writing that, you'll write M, O, Y. That means reflection in the y-axis, because M here stands for mirror line and OY stands for the line OY, or the y-axis. So for the reflection in the y-axis, we're going to measure perpendicular distances from this line. So from here to here would be 1, 2, 3, 4 units to the left. So the image would have to be found by measuring the same 4 units perpendicularly to the right, the other side. 1, 2, 3, 4. So that's how we get A prime. So B is 1 unit to the left, so B prime will be 1 unit to the right. C will be 1, 2, 3 units to the left, so C prime will be 1, 2, 3 units to the right. So once we locate the image points A prime, B prime, and C prime, all we do is connect them up with straight lines, and that will give us our reflection, right, in the y-axis. In terms of reflection in the line y equal to x, right, we will have to get actual perpendicular lines from here, measure the distance, right, to C. So C, sorry, on this side, and whatever that perpendicular distance is, you measure it on the other side. You could get this perpendicular distance using a set square, which is the triangle in your geometry set, and line it up like this, and you would be able to get a perpendicular line, and therefore you'll be able to measure from here to here, right? Your set square, you guys know what your set square looks like. It's a triangle. So if I draw in what the set square would tend to look like here for you, right? The set square is a triangle like this. So there's a 90-degree relationship here. And when you put your set square, it will enable you to get a perpendicular distance from the mirror line, which is this line here, y equal to x, to each one of your object points. And whatever that distance is, you measure it in the opposite direction. So if from here to here was 4 units, when you measure with your ruler, you measure back 4 units on the other side to get the image. Similarly, if from here to here was 3 units, you measure back 3 units on the other side to get your image point. And once you get all the image points, you connect them up. So that's how you would get your thing, your image. The line y equal to x always goes through the origin and always lies on points where the x coordinate and the y coordinate are the same. So if I didn't have it, I would have used, for example, 1, 1. That's a point where the x coordinate and the y coordinate are the same. And I could have used this one here, 1, 2, 3, 4, 5, 5. I could have used this point up here, which is 5, 5. And having these 2 points, I could draw this line and I would know that that is the line y equal to x, because on that line, the x coordinate and the y coordinate is the same. Similarly here, right, I could use the point 0, 0. That's an easy point to get. And I could also draw that line. Okay, so that's how we could draw it in case they didn't give it to us. The next reflection we are supposed to know about is the reflection of the line y equal to minus x. And we get the transformation matrix in the same way by learning the rule, right? Up here, this was the rule: interchange x and y in the line y equal to x. In the line y equal to minus x, what do? We do the same thing as we would have done before, right? But let me just get, right? Let me get yellow. Right? We interchange x and y, but then we multiply by minus 1, right, to get the image points. So up here, we had interchange x and y when we're doing reflection in the line y equal to x. But when we're doing reflection in the line y equal to minus x, not only do we interchange x and y like up here, but we multiply by minus 1 because it's in the line y equal to minus x and not the line y equal to x. Right? So they're similar rules, except that we have one additional thing to do when we're doing reflection in the line y equal to minus x, which is multiply by minus 1. So the transformation matrix here would have been this transformation matrix, because 1, 0 would give us this under these rules, and 0, 1 would give us this under these rules, right? If we interchange, 1, 0 would become 0, 1, and then we have to multiply by minus 1. So 0, 1 would become 0 minus 1 when we multiply by minus 1. Okay, 0, 1 will become 1, 0, but when we interchange, but when we do the last step, which is multiply by minus 1, 1, 0 will become minus 1, 0. And this would be the transformation matrix that we would multiply all the object points by, and the answer we got will give us the image points. So if they told us calculate, we would know what to do, right? Of course, we don't have to calculate. We could just use this rule on all of the object points and we get our image points. Okay, in this case, if we had to do drawing, well, this would be the line y equal to minus x, right? They would normally draw it for you, but if you want, you could get points, right, that would lie on this line. For example, this one and this one, right, will be a line where the y coordinate, remember, it's y equal to minus x. So if we have a point x and a point y, right, with those coordinates, x, the y coordinate will be the same thing as minus x. So here, the x coordinate here was -1. So the y coordinate will be the opposite or the negative of -1, which will be +1. So that's how I would have gotten this one here. Here, the x coordinate of this point is -2. So the y coordinate will be the opposite or the negative of -2, which is +2. So that is this point here. So I could draw my line. Of course, you could observe it also goes through 0, 0, right? So I could draw my line if they didn't give it to me by knowing that it will go through points that have those properties that I just said there. Because the line has this relationship, the y coordinate is always equal to the negative of the x coordinate, y equal to -x. So I could get points and draw the line. Then in a similar way, I would measure perpendicular distances, just like I use my set square here. I could place my set square along this line and get a perpendicular distance to the object. And whatever I get on the left, I would do the same thing on the right to get my image point. Same thing here and same thing here. Okay, so that's how you get your image for reflection on the line y equal to -x. The last one is reflection in the origin. And reflection in the origin is very unique because you're reflecting in a point, right? You're reflecting in the origin, which is what I just showed you there. That's the origin there. In all the others, you're doing reflection in a line. This one, you're reflecting through a point. And how do you actually do that reflection in a point? Well, to do reflection in a point, all you do is you measure from the point to your object point, let's say K it is, and then along that same line going in the opposite direction, you obtain your image point by measuring the same distance. So if from the origin to K was 2 units, you'd have to go in the opposite direction along that same line 2 units, and that would carry you to the image of K, which is K prime. Let's say you wanted to get the image of M. You would draw this line to M, measure it. Let's say it was 5 units, 5 centimeters. Then you would go backwards with this same line now. Go backwards, the opposite direction, the same distance. So if it was 5 units from O to M, it'll be 5 units going along this line in the opposite direction, O to M prime. And you would get M prime. And you do that for all of the image points, right? To get all the image points, and then you connect the dots up, and that will give you the image. So that's how you do a reflection in the origin. Now, our special rule for reflection in the origin will be multiply x and y by -1. So what that means is every image point will be obtained from the object point simply by multiplying it by -1, right? Multiplying both values by -1. So for example, just so that you'd understand, if I wanted to get my my points very quickly, if I observe that the point n was, the coordinates of n was 0 for x, and here, right, n is 0 and 1 for y, right? So that's my n. To get my n prime, all I would do is apply this rule. Multiply x and y by -1. So x, which is 0, if I multiply that by -1, I still get 0. And this one here, if I multiply by -1, I'll get -1. So that will be what n prime will be. But of course, we cannot just write it down like this. This is our special advantage. We'd have to find our transformation matrix, which is this here, -1, 0, 0, -1. How I got it was by utilizing my 1, 0 to give me this by applying my special rule. What is the rule in this case? Multiply x and y by -1. So if I multiply this by -1, I'll get -1, and 0 by -1 will give me 0. So that gives me this first column of my transformation matrix. To get this column here, I see what happens to 0, 1 under our special rule, R, which is multiply x and y by -1. Right? So how do I get that? 0, 1 multiplied by -1. 0 by -1 is 0. 1 by -1 is -1. So this would have been the transformation matrix that I would have to use. Remember, we cannot just do this in the exam. And then I would write down next it just like I did before, my object matrix, which I would have gotten from the points that they gave me, and I would have been able to write my image matrix here with all the points by simply taking all the x and y values I got here and multiplying each one by -1, and I will get all my image points here, right? And then I don't leave it in this version. I bring it down to a horizontal version if they want points. Now, there's something that I didn't mention to you, but let me go back up and talk about it, right? In all of our reflections, let's expand it back a bit so you would see it, right? In all of our reflections, if you notice, there's something called the sense. Now, what the sense is when you look at the vertices of the object, right? You observe, if you go alphabetically, right? If the points are going in a clockwise sense or anti-clockwise. So if I go A, B, C, D, if you notice, it's going clockwise. If I come down into the image now and I go A prime, B prime, C prime, D prime, you notice it's going anti-clockwise, right? So what happens is that the reflection in the x-axis, which is this one here, the sense is reversed in the image. So if it starts off clockwise, it ends up anti-clockwise, right? And that is for reflection in the y-axis. In the x-axis, sorry. And for reflection in the y-axis, the same thing happens. If we go clockwise, if we look at A, B, C, it's clockwise, and the image A prime, B prime, C prime is anti-clockwise. So again, the sense is reversed. You would find that if you look at it for reflection in the line y equal to x and y equal to minus x, both of them, again, the sense is reversed. But for reflection in the origin, which is the unique one because it's reflection in a point, right? What we find is that just like that's a unique aspect of the reflection in the origin, there's another unique aspect. That is, the sense is not reversed in this case. Now, let's check it out and see what that means. If I look at the object and I go alphabetically, K, L, M, N, that's clockwise for the object. Let's look at the image and see what happens. K prime, L prime, M prime, N prime. Going alphabetically, you notice it's still clockwise. So here, the sense is the same. It is not reversed. So again, that's a nice little neat little point that you could take note of. So those would be the reflections that we need to be aware of. Again, reflection in the x-axis, y-axis, y equal to x line, y equal to minus x line, and the origin. Those are the ones we're supposed to be familiar with. What we're supposed to go to next is something called rotations, right? Let's write it down. Right? So we would have looked at before translations, today, so far, reflections, and now rotations. Now reflections carry the symbol M, rotations carry the symbol R. So if you look here, you notice using R. And this is a rotation, right, with Y as the center of rotation, and you're going through an angle of minus 90 degrees. Now, let's go down a little bit and see what that means, and then we're going to come up to the drawing, right? So rotation about the origin, that is the origin as the center of rotation, has some particular information we need to know about. So let me go back up and look at this, and then we'll come back down because that would be putting the cart before the horse. Let's come back up here, and I'll tell you what minus 90 means. And this minus 90 here means rotation in an anti-clockwise direction. Because what we learn in rotation is that if the rotation is clockwise, it's considered to be a negative rotation. So I'll put minus theta. And if it's anti-clockwise, right, the rotation is considered to be positive. So use positive theta, right? Theta being the angle of rotation. So this drawing here is a example of how we could do a rotation about any point. It doesn't have to be the origin like what we're going to talk about next. It could be a point Y, X, Z, any point, and anywhere on the plane. So let's say we had in our exam, right, A, B, C, and that was a particular triangle, and they wanted us to rotate this in a clockwise direction about the center of rotation Y. So Y here would have been our center of rotation. Right? This would have been our center of rotation right there. How would we go about doing that? Well, very quickly, I'll show you what to do. So I'm highlighting in red the starting situation. So we start with ABC and we start at Y. And the first thing we'll do is to draw a line from Y to any vertex. So I'm going to draw, for example, a line from Y to E. Okay, so I'm going to do that by using red to show you what the order in which we do it in. Right, so we're going to connect. So you take your ruler and you're going to draw a line from Y to that point. And you're going to measure that distance. All right, so let's say that distance was 5 centimeters. You're going to take a note of that. Then you're going to take your protractor and you're going to put the center at Y, the baseline or the zero line from going from Y to E, and you're going to measure clockwise. Clockwise means take this line and go measure this direction. And wherever 90 degrees is, because you're going to because your rotation is 90 degrees negative, meaning clockwise, right? You're going to stop there. So let's say your protractor told you that you had to end up at this point here in this direction. Then that's where you're going to draw your line that will give you the image of A, right? Which will be A prime. So now we're going to draw a line through that 90-degree angle. And where you see the red dashes appearing now, that will be along the line A. But how do we know where A prime will be? A prime will be the same distance that A was from Y, which is this 5 centimeters here. We're going to have to measure 5 centimeters in that direction. And wherever that line up, that will give us A prime, which will be right there. And we do that same process for every single object point. So again, we're going to connect Y to C. I'm going to do that now with the red marker. Right? And that line, let's say that was 4 centimeters long. I take my protractor, put the base along Y to C, and measure 90 degrees now, clockwise, which is from here going clockwise this way. And where it ends up, which is along here, I'm going to draw a line from Y, and I'm going to measure the same 4 centimeters, and it's going to end up here. Okay, so once it ends up here, 4 centimeters, that's going to be the image of where I started from, which is going to be C prime. If I do the same thing from Y to B, measure 90 degrees, which will be going in this direction, and wherever it lands, I measure back the same distance I got from Y to B, and that will give me wherever that distance ends, which is right here, that will give me B prime. So all I do now is connect up A prime, B prime, and C prime. I'm connecting it up now. A prime to C prime, then C prime to B prime, and then B prime now I'm connecting back to A prime. And so I would end up with that triangle, A prime, B prime, C prime, which would be my image triangle. And that's how you do it in drawing method. That's a drawing method. Good, but there are special things that you could use for calculation. So for example, if they told you, listen, you need to be able to do rotations when the center of rotation is the origin, then there are certain rules, right? The first rule that you need to be aware of is that the matrix which defines a rotation about the origin through theta degrees, whatever theta is, that is 90 degrees, 45, theta is just any angle, is this transformation matrix. So you need to learn this cosine theta, minus sine theta, cosine theta. Now remember, why do we need to know this? Because all transformations besides translations, we use this formula. What is the formula? The formula is transformation matrix times object matrix is going to give us the image matrix. We did it just now where we found out our transformation matrix for reflections, whatever they were. We got the object matrix by taking all the object points and putting them vertically. And if you didn't know the trick or the words that I told you to learn for reflection, you would have had to multiply it to get the answer. Similarly, for rotation, the transformation matrix has to be found. And this is how you find the transformation matrix. Once you know its reflection about the origin and through an angle theta, you have to make up a transformation matrix using this formula here. The object matrix is made up in the same way as we did for reflections. And then you actually have to multiply it out to get this. The other thing is that theta is positive if the rotation is anti-clockwise, which we had studied up here. Anti-clockwise means theta is positive. And it is negative, that is, you're going to have a negative theta if the rotation is clockwise, which we had studied up here. Negative theta if it's clockwise. Right? So these are the things that you need to know for rotation. So for example, if they told you determine the image of triangle PQR with coordinates, and they give you coordinates of P, Q, and R respectively, under a clockwise rotation of 150. Now you could determine the image utilizing a calculation method or drawing in this case, because they didn't tell you calculate or draw, they said determine. Now, here I'm going to concentrate on the calculation method, right? Because I had shown you up here how to do a rotation. So you use that same method if you had to do it a drawing method, but we want to look at the calculation. So in the calculation, if they said, right, determine or calculate the image of these points here. So this will be P, Q, and R, right? P, Q, R, right? So that means that I could take P, Q, and R and write it here, P, Q, R. Let me expand this a little bit so we can see it a little better. Right? So I wrote down P, Q, and R here, remember. P was 2, 3, so I wrote it here, 2, 3. Q is 5, 0, 5, 0. R is 4 minus 3, 4 minus 3. So this would be the object matrix. Object matrix. But remember, we have to multiply that by the transformation matrix to get our image matrix. That's the formula that we use all the time. Look it up here. Where did I put it? We got so big. It disappeared. Look at here. That's the formula that we use all the time. So I'm just putting it back here so that you can see what we are talking about. Okay? So the transformation matrix, though, is found just 1 second. Right. Right. So the transformation matrix, how do we find that? Well, we're going to use this formula here. What is the formula? Cos theta minus sine theta, cosine theta, right? So cosine theta will be cosine of this angle here, this 150. Right? But if it's clockwise, it has to be minus 150. So you're going to have to find the cosine of minus 150. And that's how you're going to get this answer here. So our transformation matrix, let me write it out here for you. Utilizing cosine theta, utilizing this up here, let's put it in here. The cosine theta for this will be cosine, right, of theta. Now this theta, one might be tempted to put 150. But remember, it's a clockwise rotation. And once it's clockwise, then we have to assign a negative sign, minus theta, if the rotation is in a clockwise direction. So I'd have to put minus here for this, okay? So the next one we'd have to do is minus sine theta. So let's write down minus sine theta. Theta again is negative 150, negative 150. In this here, we have to find sine theta. So you have to write down sine theta is negative 150. And then cosine theta goes in this position here. That'll be cosine of negative 150 again. Right? So what you would find is when you put this into your calculator and you get the cosine of minus 150, you're going to get this figure here. Minus sine of minus 150, you're going to get this figure here. Sine of minus 150, you're going to get this one. And cosine of minus 150, you're going to get this one. Because we needed to get the transformation matrix for this rotation. Right? So when we get this, we simply have to multiply it by the object matrix, which is P, Q, and R. P, Q, and R written vertically. And when we calculate it, we're going to get the image matrix. So what I did is I went through all the calculations here that you could look at afterwards to see how you would get your answer, right? Remember, it's always row by column. So this row by this column will give you this answer here. That's the top one here, which when we work out, will work out to be this one. And then this row by this column will give you this answer here, which when you work down, you get this. Okay. To get the next one, which will be Q prime, you have to multiply row by column, which is this, and then row by column, which is this. And when you work down the two, you keep working down, you come to this answer. To get this final one, R prime, you're going to multiply row by this column, which is this, and then this row by this column, which is this. When you work this out and you keep working it down, you're going to get these answers. Right here, we did rounding off the one decimal place from here to here. And then these would be your image points, P prime, Q prime, and R prime. But remember, just like all the other times, we don't leave it like this. When we write points, we always put it horizontally. So negative 0.2, negative 3.6 will be P prime. Q prime will be negative 4.3, negative 2.5 like this. And R prime will be this, which is written here. And you observe that it is written in a horizontal manner. Okay? So that's how you do rotation clockwise. The other one was anti-clockwise of 135. So what you would have done here is you utilize your same formula, right? Which is what? Cos theta minus sine theta, cosine theta. That's the formula for finding the transformation matrix for the rotation, which is this, right? So theta now is going to change. Theta in this case is going to be 135. But if it's anti-clockwise is positive, right? Where theta is positive if rotation is anti-clockwise. So in this case, where you have anti-clockwise, that 135 is going to be positive. So in this transformation matrix that we need to come up with is going to be cosine of positive 135. Here will be minus sine of positive 135 because you're going anti-clockwise. Sine theta now, that is this sine theta here, will be sine of 135. And this cosine theta here will come here. That'll be cosine of 135. And when you calculate these figures, you got for cosine 135, you're going to get negative 0.707. For minus sine 135, you're going to get negative 0.707. For sine 135, you're going to get 0.707. And for this one, cosine 135, you're going to get this, right? So you could always check that on your calculator, right? I'm going to expand it back big again so we could see. PQ and R will be what we had here. PQ and R written down. We're getting PQ and R from up here. Remember, P was 23, Q was 50, and R was 4 minus 3. So we just write it down, 2350, 4 minus 3. And then you need to be able to multiply again matrices, as I showed you, rows by columns, to get the final answers. All right? Here we round it to one decimal place again. So P star, Q star, and R star. We use different ways to name them now because we want it to be different from the other image we got before. right? We round it off to 1 decimal place. So for example, P star would be negative 3.5, negative 0.7 written horizontally. Q star will be written like this here. And R star, this here, round into 1 decimal place. Okay? So that's how you do rotations, calculations, if you are to do it about the origin, taking into account that if it's clockwise, the angle has to be negative, and if it's anti-clockwise, the angle has to be positive. Okay? This here is if we were given, in rotation, sometimes they give us this, and it comes in multiple choice too. I've seen it in multiple choice, where they give you the object, they give you the image, they say, listen, a rotation happened here. Or they might say, name the transformation that takes the object to the image. And you have to be able to deduce it's a rotation and what's the angle. So what's the method? Well, I actually gave you the method here, but I'm going to describe it for you quickly. And I'm going to draw it out for you so that you'll see what it's all about, right? So if they give us the object and the image and they say, find the center of rotation and the angle of rotation. Or they say, tell us what transformation maps the object to the image. Well, what we could say is, all right, it looks like a rotation. And let's see if it's a rotation. So how we do it is we're going to connect a pair of object and image points. So I'm going to connect either A to A prime, B to B prime, or C to C prime. So in this case, we connecting A to A prime. So we connecting this A here. Let me get back my red. Right? Let me get back my red. So we connecting A to A prime. So you take your ruler and you draw this line that I'm moving. Right? So I just connected A to A prime. And I'm going to bisect that line. Bisect means find the middle of it, so you can measure the length and find the middle by dividing that length by 2 and marking the point right here. So you bisect it, find the middle, and then you draw a perpendicular line. You can draw that perpendicular line using your set square, right? Set square is a little triangle. So you take a triangle and you put it up on the line like this, right? And you draw the line along here. And you draw that all the way down, right? So I'm going to draw that line coming down along my set square. Good? And that's the first step. The second step is to connect any other pair of object and image points. So I'm going to connect, for example, B to B prime. I'm connecting, connect, bam. Good? And then I'm going to bisect that as well. So that means I'm going to measure the distance from B to B prime with a ruler. If it's 10 centimeters, I'll divide it by 2, so I'll get 5, and then I'll measure 5. So let's say 5 measured from here to here. I take note of that, and then I put down my set square again to get the perpendicular, because the set square is made whereby it has a perpendicular relationship. So I put it down, and I draw a line along here, right? And that will be my perpendicular bisector. Right? Perpendicular bisector. And what you notice is that these two perpendicular bisectors are meeting at a point. Yeah? That point is the center of rotation. So this method allows you to be able to find the center of rotation when you have the object and the image. Right? If somebody said, so could I have connected C to C prime and then bisected that? Would it have that line intersected at X as well, at here as well? And the answer is yes, it would have intersected right there. And that would have been the center of rotation. So now that we have the center of rotation, all you have to do is find the angle of rotation. So that's easy. All we do is connect to an object point. So let's say I connected it to A. So I took my ruler and I pencil and I connected from my center of rotation to A. And I then connected it to the image of A, which is A prime, which is along this line now I'm drawing here. Right? So now I have the lines that connected A and A prime. And then what do I do after that? I measure the angle. Right? That angle there. And in this case, the angle worked out to be 90 degrees. And if you notice, I'm going in an anti-clockwise direction. So it would have been positive 90 degrees. So that method is the method that we use to calculate, firstly, where the center of rotation is when we have the object and the image, and also to deduce what is the angle of rotation. Okay, so that's a very important skill that you need to be aware of. The next transformation that we look at is one that is called enlargements. Right? So far we looked at translation before. Today we looked at reflection, rotation, and now we're looking at enlargement. Now enlargement, right, usually ends up with the image being larger than the object. Sometimes you could have an enlargement that causes the image to be smaller than the object. We say that the image is diminished. Okay, but we're going to look at the first case, which is the case that most people would start off with, whereby you start with an object and you end up with a larger image, right? Now, in rotation, there are two things we need to be aware of: the center of enlargement, which is this point here, and the scale factor, which is our multiplying factor. So this here is the center of enlargement, and we have our object, which is ABC. Now, let's say we were going to use a scale factor of 2, right? That means K is equal to 2. Right? So that if I wanted to perform an enlargement on this using drawing method, I would have connected, for example, O to A. Right? So connecting O to A like that. And I would have measured that. So let's say OA was 2 centimeters, right? 2 centimeters. Then how would I know how to get from O to A prime? Well, the answer is simply use the scale factor. So let's say they said the scale factor is 2. We're going to get the distance from O to A prime. I would have to take this 2, let's say it's 2 centimeters, and multiply it by the scale factor. So this would be the 2 centimeters here, multiplied by the scale factor K. In this case, K was 2. So I'll multiply 2 by 2 and that'll give me 4 centimeters. So what I'd have to do now is to measure from here to wherever I'm going, which is the image of A, to get to A prime, I'd have to measure 4 centimeters. So if this is 2, I'd have to double it. So I get 2 here and 2 more. So in all, I'd go 4 centimeters. So now I'd have to go 2 more. And that would land me here. That'll be A prime, which would be 4 centimeters. And in that way, I could get the other image point. So let's say from here to here was 1 centimeter. Then I'll multiply that 1 by the scale factor of 2. So 1 by 2 will give me 2. And therefore, the distance from here to here would have had to be 2. 1 here and 1 more here, which would have given me this point here. So I'd have to measure that distance, 2 centimeters, until I got to this point. Let's say when I measured from O to C, I got 1.5 centimeters from here to here. Then I'd have to multiply that 1.5 by the scale factor 2 to get the distance to go to the image. 1.5 by 2 is 3 centimeters. So from here, I'd have to go 3 centimeters out, which would be the first 1.5, and another 1.5 would carry me to the 3 centimeter mark, which would have given me C prime. Then all I do now is connect the dots up. I'm showing you how I connecting those dots up there. And I would have gotten my image. In this case, the image is larger than the object. All right. And for scale factor, if they are just giving me these two and they tell me find out the scale factor, I could get that scale factor 2 ways. I could use the image and object lengths themselves, or I could use the distances. All right. So that's what this is saying. To get the scale factor, I could divide the distances like OA prime over OA, and the answer would give me the scale factor. Or I could use the actual lengths on it. So I could have said A prime, C prime divided by AC, for example, would give me the scale factor. Or A prime, B prime divided by AB, that will give me the scale factor as well, same scale factor. Or B prime C prime divided by BC will also give me the scale factor. I use a general rule to get the scale factor. All I do is take the image distance or image length and divide it by the object distance or object length. So it's really image over object always gives us the scale factor, but it has to deal with the length. Okay. While I'm on that topic, before I continue with scale factor, there's a very important one. I'll put an asterisk by it because this comes in exams and most people don't know how to do it. And I'll put it in this way. Here I had image length. I'm going to write something else. I'm going to write image area. And I'm going to put it over object area. What most people don't know is that this calculation here, where we interchange area for length, remove the length and put the area instead. If we do this calculation, we are not going to get K, we are going to get K squared. Very important bit of information. Most people don't know this, right? Or even if they know it, they forget it. The teachers don't emphasize it and it comes in the exam, right? So you need to have this relationship in your brain. It does not give you the same answer. The area relationship is different to the length relationship, okay? Now, I'll come back to this here. I want to show you something else. Whereby, what we just looked at, if we start off with the object here, and we have a scale factor of 2, it carries us out further, right? And we actually end up going out further, and ending up with a larger object, right? Sometimes, as I mentioned to you, you could end up with a diminished or smaller image, right? So I said object just now, that was a mistake. So sometimes you'll end up with a larger image. In this case, it was a larger image here. But sometimes you could end up with a smaller image, which is known as a diminished image. That happens when K is a fraction, meaning a half, a quarter, a third, right? 2/5. Whenever K is a fraction, you're going to end up with a diminished image. Because instead of multiplying by K here, which is 2, you have to multiply by K here, which is a fraction, and that means you're going to get a shorter distance. So if the original distance here, OA, was 2 centimeters, if K is a fraction, let's say in our second case, OA was still 2 centimeters, OA prime, if we look in, let's use star, A star, which is this here, A star, right? That will be the same 2 centimeters we started with, right? Our object distance times the scale factor now, K. But the scale factor is no longer 2. In our second example, let's say the scale factor was a half, right? Let's say K was equal to a half now. Then our image distance is now going to be 2 times a half, and 2 times a half is 1 centimeter. So it means that the distance I'm going to measure to get A here, A star, would be 1 centimeter. So that means that I am going to start to get a smaller image by doing the same thing with B and C. So I'm going to get a diminished image. Okay? So that's important. But sometimes you could even get images on this side. So we have the object here, and then we end up with the image on this side. And that happens when the scale factor is negative. Okay? So if, for example, in this question, we start off with PQR, right? So look at it there, PQR. And if you notice, look where the image is here. That happens when your scale factor is negative. Here, -2 or -1/2. So for example, if we had OP from O to P as 1 unit, let's say 1 centimeter, 1 centimeter, to get to O, in this case here, to get to our distance from O to P prime, right? How we do it is we have to go not in this direction like we are done for these here, same direction. We have to go in the opposite direction. So if O to P is going this way, if the scale factor is negative, then O to P prime will be that way, opposite direction. So what we do to get the distance we have to travel, we multiply OP, which is the 1 centimeter here, right, by our scale factor. It's always multiplied by the scale factor. So the scale factor here is -2. So when you multiply the original distance OP, 1 centimeter, by the scale factor -2, you're going to get -2 centimeters. Now, what that means is we're going to move 2 centimeters in the opposite direction. And negative means opposite to what we started off with. So if this was 1 centimeter going this way, we'd have to go 2 centimeters in the opposite direction to get to P prime. So that's why we go 2 centimeters, 1, 2, and we get P prime. So we're going to do the same thing. So if this is OR, we're going to go twice the distance to get our prime in the opposite direction. If from here to here is OQ, we go twice the distance to get Q prime. And that's how we get the image on the other side. If you have a negative scale factor, but there's a fraction, you go the opposite direction, but half the distance. So let's say here was 1. You'd have to go half of that if the scale factor is -1/2, but in the opposite direction. So you'd have to go 0.5 or half of a centimeter, not this way, but this way, to get to P star. And you would do that for all of them and therefore end up with a diminished image, but on the other side, if the scale factor is negative. Now, that's drawing. But what about if we're going to do it by calculation? Because if you notice, this is relative to the origin. And just like rotation, when you have a special transformation matrix, when everything is from the origin, rotation about the origin, that's the cos theta minus sine theta cosine formula that we learned earlier. For enlargements, there's also a special scenario when you have enlargements from the origin. So for example, if we have an enlargement with the origin and scale factor k, then the matrix that would define that, or that would enable you to do calculations, would be formed by noting that enlargement is E. When it's done from the origin O as the center of enlargement with a scale factor k, then the transformation matrix that you could use would be K00, K. Right? So that's why you see me using K00, K. That means that in this case, the scale factor we're using is the -2, right? And all we have to do is take this, multiply it by the object points, and we get the image points, all right? And these would be the image points. If we wanted to do a calculation to get the image points from -1/2, what we would do is utilize the same formula, K00, K, but K is now -1/2. So we're going to put that here, -1/2, 0, 0, -1/2. Just change the numbers to what the scale factor is. And you're going to get the transformation matrix that you require, which is this, multiplied by the object matrix, which is this. And when we work this out, we're going to get the image matrix. All right? That will give us our image points. So this is enlargements. Now, there's a special transformation that you need to know about. It's known as a glide reflection. So this, what we're looking at here, is a glide reflection. Right? And a glide reflection is really a translation and a reflection in any order. So you do either do a translation followed by a reflection, or reflection followed by a translation, and that is known as a glide reflection. So for example here, if I started with this object and I did a translation first, 7, 0, which means take each point and simply move it 7 units in the X direction and then 0 units in the Y direction, which means move 7 across. Then that means that I would have to move each one of these 7 across. 1, 2, 3, 4, 5, 6, 7 would carry me to A prime from A. From C to C prime would mean move 7 again. 1, 2, 3, 4, 5, 6, 7 in the X and 0 in the Y, which would carry me here. Right? And then, of course, B to B prime would be 7 again in the X, 0 in the Y. 1, 2, 3, 4, 5, 6, 7 in the X, and 0 in the Y means stay right there. Don't go up or down. Okay, and then we connect these up, and that will give me my translation. And then if I did a reflection in the X-axis, this is the X-axis, this would reflect to here. Now, that combination is known as a glide reflection that carries me from here to here, because it's a translation followed by a reflection. But what is very instructive to note is that if we do the reflection first in the x-axis, starting from the object, followed by the same translation of 7, 0, we're going to end up with the image in the exact same position. So this image and this image are exactly the same, right? So this type of transformation is known as a glide reflection. And as you can see, it could be obtained by doing a translation and a reflection in any order. Here, the translation was done first, followed by the reflection. And here, the reflection was done first, followed by the translation. I've seen them put this in a multiple choice and ask you, what is the one transformation that takes the object and carries it to the image? And you have to come up with glide reflection is either option A, B, C, or D. And that's how you would know what is the correct thing. All right. So those people who are not here and missing these things, I hope they cover it, otherwise. So this is a glide reflection, which comprises of two transformations. The next thing we go on to is something called linear programming, right? And linear programming is a type of maths where they give you conditions, and then you are required to draw on a graph page these conditions, and then you either have to shade out the things that you want or the things that you don't want. The things that you don't want is known as the complement region, and then answer questions, usually find the maximum or minimum of something. So I put up one here, a basic one to remind you about it. And here they gave you the conditions. Sometimes you have to figure it out, right? So here they said 3 conditions are represented by the following 3 inequalities. So they gave us the inequality: x is greater than or equal to 1, y is greater than or equal to 2, and y is less than or equal to minus 2x plus 7. Good. They want us to determine the maximum value of p and the minimum value of p if p is equal to x plus 3y. So the first thing we have to do is let me reduce this a little bit so you'll see. Right? The first thing we have to do is write down all the inequations given, which is x is greater than or equal to 1, y is greater than or equal to 2, and y is less than or equal to minus 2x plus 7. So I wrote down those here. Then the next thing you have to do is to write down all the equations that come from these 3. So the equation would be this equal part, which would be x equal to 1. From here, y equal to 2. And from here, the equation part will be y equal to minus 2x plus 7. So we have to then take these and draw it on a graph. So x equal to 1 is, I wrote it here. Y equal to 2, I wrote it here. Y equal to minus 2x plus 7. So let me fix that. This should be minus 2x plus 7. Right? Minus 2x plus 7. So I wrote it down here. Y equal to minus 2x plus 7. So I'll expand the screen again. Right? So we can see it a little bigger. Okay. So after you take the inequalities and you draw and you come up with the equalities, we draw them out on our graph. So we draw our graph, right? And we have to draw the line x equal to 1. So x equal to 1 is a line that is going to go through where x equal to 1, which is here. See, x equal to 1. And it's going to be parallel to the y-axis. Then we're going to draw a next easy one, right? X equal to 1 was easy. Let's draw y equal to 2. So wherever y is equal to 2, this is the y-axis, which is here. We're going to draw the line y equal to 2, which is this line here, right? That passes through the y-axis. So we got 2 lines. This one here, right? And this one here. Okay, great. Now we have one more line to draw. The line y equal to minus 2x plus 7. That is not so easy to draw like these lines, okay? What you need to do is to draw up a little table that enables you to get 2 points from this. So what we did is we drew up this table here, whereby we choose values for x. You don't need to do 3 points. That was a little over the board. You could just do 2. So a nice easy point is always where x is equal to 0. And you put that into this equation here. So let me write that out for you. If y is equal to minus 2x, right, plus 7. If I'm going to use x equal to 0 here, then it means that y is going to be minus 2 times 0 plus 7, right? And minus 2 times 0 is 0. So y is going to work out to be 7, which is this 7 here, right? So we see how you get the 0.07. Let's see how you get the 0.15. Write back the equation. Y is equal to minus 2x plus 7. But now x is going to be 1. So you're going to put 1 right here. So let's put a 1 in. Plus 7. So what is going to happen here is going to get minus 2 by 1 is minus 2 plus 7. And if you take minus 2 and plus 7, what you're going to get is plus 5. So that's how we got this 5 here is this 5 here. So we were able to get 2 points, 0, 7 and 1, 5. And if we plot those 2 points and draw a line through them, then that will be this line, y equal to minus 2x plus 7. So we're going to use that table to get here, right? 0, 7 means 0, 7, that's this point. And 1, 5 means go 1 across and go 5 up, which is this point here. So now that we have these 2 points here, we could draw this line here, y equal to minus 2x plus 7 by connecting up the dots. So you connect up this dot, and you keep coming down, and that line is going to be the line y equal to minus 2x plus 7. So that's the first part. That's the first part. Draw all the equalities, right, which is the lines that represent or that come from these inequalities. So we draw it here. X equal to 1, y equal to 2, and y equal to minus 2x plus 7. Good. Now, we're going to shade out, firstly, what we wanted, right? So you have x greater than 1. So if this is x equal to 1, x greater than 1 will be everything to the right. So that's why you're shading out. That's why you're seeing these lines here. See these? That is these here. Right? So you shade it out. That's what we wanted. Then let's look here. Y greater than 2. So if this is a line y equal to 2 here, this one here that I'm showing you the cursor, y equal to 2. If I am interested in y greater than 2, that means I have to shade above the line. So that's these lines going here, above the line. See those lines there? That's the lines that shading out y greater than 2. Good. So the next one is this guy here. And that one is y less than minus 2x plus 7. So if this is the line y equal to minus 2x plus 7 here, and we want to get less than would have to be below that line. So that's why you see us shading these lines here. Those lines there going across from below that line y equal to minus 2x plus 7 is the area that y is less than minus 2x plus 7. So we shaded that out. So what is going to happen now to satisfy all these three? We're going to have to look for the overlap of all the shading that we did. And of course, that's a bit challenging, but if you look closely, you will see that those three areas that overlap, they would overlap in this region here, enclosed by this triangle. This is A, that's B, and that's C. So this triangle is A, B, C. And the common region which satisfies all these three inequalities would be on the lines and inside of here. Good. So why do we need that common region? Because we have to answer these questions. The questions is, what is the maximum value of P and what is the minimum value of P? Now the maximum and the minimum value of P would have to be on the extreme points because maximum and minimum are extreme values. So it cannot be points inside here. It have to be points on the border, the furthest points, the extreme points to get the extreme values, which are known as the minimum and maximum. So the minimum and maximum values are going to come from these 3 points here, right? Now we're going to go and find these minimum and maximum values, and then I will come and explain this one here for you, right? Which is another way to do it. So what we do is we select the point A, because a minimum or maximum could be, would be here, right? Here's a likely point, which is 1, 5. So A, 1, 5, right? We did that. This is this one here. We're going to be looking at the point B to be able to locate and find out if that's a maximum or minimum. And that's going to be the point 1, 2. So that's B. And then we're going to be looking at C, which is the point 2.52. 2.52. And I'm going to put it here. That's C. Good. And what we're going to do is we're going to take these values for A, B, and C, because that's where maximum or minimum would come from, and put it into the formula P is equal to X plus 3Y. What is the formula? P is equal to X plus 3Y. That's the formula that we're going to be looking at. Right? P is equal to X plus 3Y. So let's go with that. Remember, this is a X value and this is a Y values. So all of these will coming vertically down will be X values and Y values. So if P is equal to X plus 3Y, and for A, X is 1, then 1 is going to go here, and Y is 5 for A, point A. So 5 is going to go here. So P is going to be 1 plus 3 by 5, which is working out to be 1 plus 15, which is 16. So this is one potential answer for P. Let's do the same thing for B. X is 1 in this case, so 1 is going to come here, and B, Y is 2. So 2 is going to come here, so 3 by 2. So it's going to be 1 plus 3 by 2, which is 1 plus 6, or 7. So this is a potential maximum or minimum as well. Then we're going to do the same thing for C. X is 2.5, Y is 2. So X is 2.5, Y is 2, here and here. And we're going to work that out. So that's 2.5 plus 3 by 2, which is 6. 2.5 plus 6. That's going to be a potential maximum or minimum. But when we compare these three, the maximum is this, and the minimum is this. So our maximum P is going to be 16, and our minimum P is going to be 7. Because these are the points where these maximum or minimum, which are extreme values, will take place. And that is what they wanted. Good? Now, there's another way that we could have found these 3 points, which is where the extreme points would be, or the common region. And easier to see where the common region would be by using another method, which is called shading the complement regions. So instead of shading what we wanted, right, which was X greater than 1, for example, we would have shaded what we did not want. So we didn't want X less than 1. Right? We wanted X greater than 1, so that means we didn't want X less than 1. So we shaded out that as going this way, which is to the left. X will be less than 1 on this side. Here we wanted Y to be greater than 2. So if we're shading out what we did not want, we'd have to shade out Y less than 2. So if this is Y equal to 2 here, that line, Y less than 2 will be below it. So we shaded that out. Y less than 2 will be below. And lastly, if we wanted Y to be less than minus 2x plus 7, and this is the line Y equal to minus 2x plus 7, then if we wanted Y to be less than minus 2x plus 7, let's shade out what we do not want. We don't want Y to be greater than minus 2x plus 7. So Y greater than minus 2x plus 7 will be above this line here. Above the line Y equal to minus 2x plus 7 will be the area where Y is greater than minus 2x plus 7. That'll be above it, like here. So if you notice, we shaded out all the regions that we do not want or we did not want. So therefore, if you shade out all the things you don't want, then a clear region would come out signifying what you do want. This would be the common region that you do want, where everything would have been satisfied. And of course, the 3 points again would represent the points where maximum or minimum of any function would occur, because these are the extreme values of the common region. Okay, and we would have proceeded as usual. So that's a good reminder of all the different points and philosophies and ways of working out linear programming questions are about. The next thing we look at, right, we're coming down to the end here now, would be distance and speed time graph, right? So the first thing is we're looking at distance versus time, right? That's an important study that we need to take on. It's known as distance versus time graphs. So let's look at distance versus time graphs, and this could come in the exam as well. So a couple little things. Let's talk about speed, right? A body is traveling with constant or uniform speed, right? If it travels equal distances in equal intervals of time. That means that the distance traveled will be proportional to the time. Now, what does it mean by equal distances in equal intervals of time? Like I did a little example here for you. If at time t equal to 0, which is you didn't start as yet, the distance covered is 0. If you travel for 1 second and you see that you travel 10 meters, then if you travel for an additional second, meaning 1 more second, which is 2 seconds, you should travel 10 more meters, which would mean that you travel 20. If you travel an additional second more, which is 3 seconds in all, you should travel 10 more again, which is 30. And what you notice is in that every equal interval of time, that is every extra second, we are traveling equal distances or 10 more meters. So every 1 second, we travel 10 additional meters. And this here is known as constant speed. When we are traveling a manner that equal distances are being covered in equal intervals of time. That is known as constant speed, and a graph of distance versus time will go through the origin. So if they give you a graph like this and say, what is that? Constant speed, constant acceleration, constant velocity, you should be able to say constant speed. Okay, because it's going through the origin, and we say that the distance is proportional to the time, and so this is constant speed. Now, what you need to know is that the gradient of a distance time graph that looks like this, right, where we will always give us the constant speed, right? So if I find the gradient of this, I will get the constant speed, and there's a formula. Speed is equal to distance over time. This speed is constant, or it could also be known as average speed. So sometimes you need to use this equation as it is, or you need to be able to manipulate it to your benefit. So here, for example, let's say a model train travels 75 meters at a constant speed of 30 meters per second. Calculate the time taken for the journey, right? Now, this is the formula that you know, speed equal to distance over time. But here, they are not asking you for speed, they are asking you for time. Calculate the time taken. But this is the formula that you know. So you have to know how to manipulate the formula, right? Or you have to be able to put the figures in and solve, right? Because you know how to solve equations. But from this equation, you should be able to know or to figure out that if speed is equal to distance over time, then time is distance over speed. So to get the answer, right, to get the answer for your time, which is this, all you have to simply do is take your distance and divide it by speed, 75 divided by 30, and that answer that you get will be your time in seconds, right? Because the unit here is meters per second. In the second example, right, something that you could look at for constant speed, they say a train travels 100 kilometers at a constant speed of 66 and 2/3 kilometers per hour, right? Now, this kilometers per hour could also be written like this, kilometers per hour, right? It then travels 75 kilometers at a constant speed of 37.5 kilometers per hour, and a further 25 kilometers at a constant speed of 16 and 2/3 kilometers per hour. Good? Draw a distance time graph and then determine the average speed. Okay, but there's something strange here. Every so often the speed is changing. It's not a constant speed. It's constant for a while and then it keeps changing. So in order to solve this in our solution, what we're going to do is we're going to break it up and find the times for each part of the journey, right? So seeing that time is distance over speed, we're going to keep taking the distances over the speeds and getting the time. So distance 100 divided by the speed 66 and 2/3 gives us 1.5 hours for that part of the journey. For the next 75 kilometers, the time taken would be 75 over 37.5 according to the formula distance over speed. That takes an additional 1.5 hours. And then for the final 25 kilometers at this speed, the time would be 25 over 16 and 2/3. That gives us 1.5 hours. So I made a mistake there. So this was the first time. The second time would have been 75 over 37.5, which is this. And the third time would have been 25 over 16 and 2/3, right? And of course, these would be the times to cover each additional distance travel. Good. So we can make up a table, right? We can make up a table from this. Now, the table is going to be made up of total distances traveled and total times taken to cover those distances. So in the first instance, you travel 100 kilometers and you took 1.5 hours to do so. In the second instance, you had traveled 75 more. So the total distance would have been 100 plus 75, 100 from the first part of the journey plus the additional 75, giving you 175. And the total time taken would be the 1.5 from here plus the 2 hours it took to cover the 75, right? The 2 hours it took to cover the 75, which gives us 3.5 in all. And then the final part of the journey was 25 more on top of this 175, which gives us a total of 200. And therefore, the total time, seeing that that took an extra 1.5 hours, would be 3.5 from here plus 1.5 extra, which means 5 hours in all to cover the whole distance. So this table here will enable us to draw a distance time graph to represent this journey. So I'm going to take this table and carry it a little further down here. And that is what we're going to use to draw the distance time graph. Okay, so for a time of 1.5 hours, you travel 100 kilometers. So 1.5 hours, 100 kilometers. So that'll be our first 100 kilometer. That'll be the line to represent it. Good. For the second part of the journey, which would be 175 kilometers in all, taking a total of 3.5 hours. So 3.5 hours will be here. 175 would be right here, smack in the middle of 150, and 200 would be 175. That'll be the point that we go into from here. Good? And that will be the next 75 kilometers we have traveled. To get this last point here, we'd have to use these two, 200 and 5. So after 5 hours, we would have gone 200 kilometers. So 5 hours is here, we would have gone 200 kilometers. So that would be our last part of the journey. So this would be the graph that they wanted. Of course, you have to set it up with your scales and whatnot, and you label it and all that properly. And then they say determine the average speed of the journey. How do you get average speed? Well, average speed is always gotten by this calculation. Total distance traveled divided by total time taken. The total distance traveled is the 200. The total time taken is the 5. So it'll be 200 kilometers over 5 hours, giving us an average speed of 40 kilometers per hour. But you don't always have constant speed like what we are looking at here for this journey. Sometimes you have variable speed, right? Now, whenever you get this in your exam, they will give you, or if you ever get it, they will give you a relationship between the distance and the time, okay? That will enable you to come up with a table. But you have to know, to do these types of questions, you have to know something very particular, which is that the gradient of a chord on the distance time graph is the average speed, and the gradient of a tangent at a point on the distance time graph is the actual speed. So these two things are quite important that you need to memorize for variable speed, right, when you're doing distance versus time. Now you're going to have to learn something like this for the last part of our class today, which is variable acceleration. But let's not jump there quite yet, right? Let's look at the example. In this example, it said the distance d in meters moved by a particle from a starting point at time t seconds is given by the formula distance is equal to 4t plus t squared. Fill in the value for d when t is 6. Okay. Well, when t is 6, how do we get this point here? We're going to put t at 6 here and here. So I put t at 6 here, and I put t at 6 here. Right? So it'll be 4 by 6 plus 6 squared. 4 by 6 plus 6 squared. That's 24 plus 36, which is 60. So that means we have to put 60 here or simply put it here. So that would have been our answer for this part by filling it into the diagram. Then they said, draw the graph of that function for the domain t between 0 and 8, including 0 and including 8. So we have t between 0 and 8, including 0 and 8 here, and we have all the values. So knowing that, we could plot these points here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, for example, 0, 0 would be right here, right? 1, 5 would be here, 1 across, 5 up, and so on. 2, 12 will be 2 across, 12 up. And that will give us these points which we could draw a nice smooth curve through using our French curve, right? Or if not, you'll have to draw it freehand. And then they ask us to calculate some things, and whereby we would have to use the formulas that we learned, right? One of the things we had to calculate was the average speed of the particle for the last 4 seconds. The last 4 seconds, I'll expand it so you'll see it a little better. The last 4 seconds will be from here to here. And to get the average speed, you may have remembered that to get average speed, let's see what we have to do to get average speed, right? The gradient of a chord on the distance time graph gives us the average speed. So we'd have to draw, right? We'd have to draw a chord between t equal to 4 and t equal to 8, right? That is between the distance, the time, sorry, that we need. And we're going to have to find the gradient of that chord, right? And that will give us the average speed. So how do you find the gradient of any line? There's a formula. Y2 minus Y1 over X2 minus X1. So I'm going to use this as my X2, Y2, 1 point on the chord, and this one as my X1, Y1 on that chord, and I'm going to find my gradient, which will give me my average speed. So Y2 is going to be 96, and I have to take away Y1, which is going to be 32. So that's this. And I have to divide that by X2, which is 8, take away X1, which is going to be 4. And when I do the division, the answer I get here is going to be my average speed, which is 16 meters per second. The other part of the question asks, what is the speed of the particle at 2 seconds? Well, how do we get that? The gradient of the tangent at a point, in this case, it will be at the point where t is equal to 2 seconds, will give us the actual speed at that time, which is 2 seconds. So we just have to locate the gradient. In this case, I think they drew the gradient for us, or we would have to draw it, which is a line that is going to touch the graph at the point where time is equal to 2, right here only, right? So you're trying to best touch it there alone, and you have to find the gradient of that line, right? So you're going to use the same formula. Gradient is y2 minus y1 over x2 minus x1. We're going to call one point here x2, y2, and this point here x1, y1, and we're going to work that out. So y2 is going to be 27, y1 is going to be 0. So y2 minus y1 will be 27 minus 0. Good? x2 minus x1 is going to be 4 for x2, 0.6 for x1, right? So it's going to be 4 take away 0.6 for x2 minus x1. 4 take away 0.6, and that calculation is going to end up with our actual speed at the time t equal to 2 seconds, which is 7.9 meters per second. Okay? That would cover what you need to know for distance versus time graphs. The last thing we're looking at now is velocity versus time graphs. Okay? And there are certain things we need to know. Velocity is distance over time or displacement over time. Acceleration is the rate at which velocity increases. So it's velocity change over time taken, which could be written as v2 minus v1 over t2 minus t1, right? Where v2 is the final velocity and v1 is the initial velocity. T2 is the time to reach the final velocity, and t1 is the time taken to reach the initial velocity. So you need to learn velocity, which is very similar to speed, except that it goes in a particular direction, distance over time. And we already know the formula speed equal to distance over time. So this should be very familiar. Velocity is distance over time as well. But this is a new one. This is when your acceleration or accelerating or your speed is increasing. This is the formula. Change in velocity over the time taken, or v2 minus v1 over t2 minus t1. The unit of velocity we know is meters per second, but this is a new unit that you may not have remembered, which is a unit of acceleration, meters per second squared. Now, if a car is speeding up, we know it's accelerating. But if it's slowing down, it is said to be decelerating or retarding. And what happens is that a negative acceleration would be obtained, and that is called deceleration or retardation. So anytime we calculate acceleration using this formula and we get it to be negative, it means then that we are decelerating. All right, so that's important. So those are the things you need to know here. Let's look at a quick example. If a car is starting from rest and it accelerates to a velocity of 6 meters per second in 5 seconds, calculate the average acceleration of the car. Okay, now average acceleration or acceleration is this: v2 minus v1 over t2 minus t1. v2 is the final, v1 is the initial velocity. So if the car is starting from rest, that is going to be v1, and it accelerates to a velocity, which is going to be v2. So v2 is going to be 6, and v1 is going to be rest. Now, what does rest mean? It simply means that v1 is going to be 0 meters per second because it's at rest, it's not moving, right? And t1 is going to be, that's not going to be t1, that's going to be t2 because that's what the time that it takes to reach v2. t1 is going to be the time that it takes to reach this velocity, which means t1 is going to be 0 seconds because even before you move, you had that velocity of 0. So utilizing these things, you're going to be able to find your average acceleration from this formula. v2 minus v1 will be 6 for v2 minus 0 for v1. So v2 minus v1 will be 6 take away 0 divided by t2 minus t1. t2 we know is 5, take away t1, which we know is 0. So when you do this calculation, you're going to get your acceleration, but remember that your unit is meters per second squared. All right, so that's a nice, easy one. In your exam, right, they tend to bring things involving graphs like this when you're having velocity time graphs, right? So let's look at it. They say if a car is slowing down, we say it is said to be decelerating. So like here, this car will be slowing down. So let me show you. Here, the car is speeding up. In other words, its velocity or speed is increasing. Here, the car is moving at constant or uniform speed or velocity. Why? Because the speed is not changing. The velocity is one level. It's flat, right? So on a velocity or speed time graph, right? This is what we have to look at, right? As compared to a distance versus time graph. Remember, you have to look at the two and remember what you're looking at. So in a velocity versus time graph, if you're going up like this, you have uniform acceleration. That means your speed is increasing. Here, your speed is uniform or constant. That means you have no acceleration because for acceleration to take place, you must have a change in speed or velocity. Then what is happening here? You're slowing down. You're starting from here and coming down to 0. That means you have uniform retardation because it's a straight line, or uniform deceleration, right? So you're supposed to know about this. Very importantly, if you have a velocity versus time graph and they ever ask you to find the total distance traveled, you need to find the area under the graph, right? You need to find the area under this graph. So if you wanted the total distance, you'd have to add up all these three. You'd have to add up this triangle, this rectangle, and this other triangle's area, and that would give you the total distance traveled, right? So this is an important bit of information to remember. So let's say you were posed with a question like this, right, in your exam, and they said a car starts from rest, so it's starting from right here, and it accelerates uniformly to a speed of 30 meters per second in 5 seconds. So in 5 seconds, which is from here to here, its speed is going to go up to what? 30 meters per second. So that's going to be the line that represents that first part. It maintains the speed for another 10 seconds. So you see this 30, it's going to maintain it. It's not going up, it's not going down, it's maintaining it for 10 seconds. From 5, 10 more seconds on top of 5 will carry to 15. So it's going to go from here to here, 15. Then what happened? The brakes are applied and it decelerates uniformly, which means a straight line to rest. To rest means it's going down to a speed of 0 meters per second in 7 more seconds. So 7 on top of 15 will carry to 22. So between here and here is 7 seconds, but that's 22 in all. And it's going to come all the way down until it reaches 22. So what that is saying is that this is going to be the shape of your velocity time graph for this situation. So draw a velocity time graph to show the various segments, which is what we just did here, and determine the acceleration in meters per second squared during the first 5 seconds. How do we find the acceleration? Remember, the formula for acceleration, right, or average acceleration is V2 minus V1 over T2 minus T1. That's the formula we're using that was given to us earlier. So if I'm starting here and ending here, my V2 will be 30 and my V1 will be 0. So V2 minus V1 will be 30 minus 0 over T2 minus T1. I'm starting here and ending here. So this is my T2, my time, 5. And my T1 is going to be 0. So T2 minus T1 will be 5 take away 0. T2 minus T1, 5 take away 0. When I work this out, I get 6. And the answer is going to be meters per second squared, because remember, the unit of acceleration in our studies, when the time is in seconds and the speed or velocity is in meters per second, the unit of acceleration will be meters per second squared. So the answer here is 6 meters per second squared for this first one. What about the retardation during the last 7 seconds? Well, the secret there is to work out what the acceleration is during the last 7 seconds, which is from here to here. And if it is negative, then we know it is a deceleration. So our final velocity, if we start here and end here, will be 0 because you're coming down to rest. And our initial velocity, V1, will be 30. So V2, which is 0, minus V1, which is 30, will be 0 minus 30 on top for this part. And T2 minus T1, T2 will be the time here, which is 22. T1 will be the time here, which is 15. So T2 minus T1 will be 22, take away 15, which goes below. This is negative 30 over positive 7. And that gives you an answer of negative 4.27 meters per second squared. Now, this negative 4.27 is really the acceleration. So if we are given the answer for retardation, we'd have to say the retardation, right? Retardation is not minus 4.27, but simply 4.27. This is the acceleration. So let's put A, right? What we were calculation is A. Same thing here, E, okay? So if the acceleration is negative, then that means that we are decelerating. That is to say that the deceleration or the retardation is 4.27 meters per second squared. All right, be aware of that. The total length of the journey in meters is what we learned. We had to find the area of the shape. Now you could find the area of the shape by finding the area of a triangle, a rectangle, and another triangle and adding them. Or you could find it by using the equation for the area of a trapezium. This is a trapezium. How you find that is you say a half multiplied by the sum of the length of the parallel sides. So this is a parallel side and this is a parallel side, because if you extend them, they'll never meet. So these are the two parallel sides of the trapezium. This here is 10 and this here is 22. So that's why I'm adding up the lengths of the parallel sides. And then when you do that, you multiply it now by the perpendicular distance between those parallel sides, which will be this distance here, and that's 30. So that's why 30 goes there. So the area of a trapezium on a velocity time graph here, this is a trapezium, would give us in this instance the distance traveled, and the area of a trapezium is a half the sum of the lengths of the parallel sides times the perpendicular distance between them. And that gives us 480 meters when we work it out. The last one was the average speed of the whole journey. The average speed is always the total distance over the total time. So let me take out that. Total distance over total time. And the total distance D was 480 from here. And the total time from here to here is 22. right? So we're going to put that 22 below. And when we divide it 2, we're going to get the average speed, which is working out to be 21.8 meters per second. Okay, and the final thing for this evening would be when we have variable acceleration, right? This here is constant acceleration, right? What we were looking at here, constant acceleration here or here, right? But there are sometimes when you have variable acceleration, when the graph is not a straight line. If you draw velocity against time, if you draw velocity against time, sometimes you get a curve, and that is going to be a case where you have variable acceleration, right? When it's you're not going to get that constant straight line behavior. Now, there are 2 points you need to know for that, 1 and 2. One is that if you have a velocity versus time graph like this, velocity versus time, right? Then the gradient of a chord on this velocity time graph gives the average acceleration for that time interval, and the gradient of a tangent at a point on the velocity time graph gives the actual acceleration. Now, if you remember before earlier, we had something similar to this for distance versus time graphs, and now for velocity or speed versus time graphs, you have something similar. Be aware that they are similar but not the same, so you have to make a particular note of that and memorize it to suit, right? So for velocity versus time graph, the gradient of the chord would give us the average acceleration over a particular time, and the gradient of a tangent at a point in time would give us the actual acceleration at that time. So in this particular case here, they gave us a relationship between the velocity and the time, and they wanted us to draw the velocity time graph for v for the domain t between 0 and 8, including 0 and 8. So you would have taken values of t between 0 and 8, substituted here, and get values of v, right? And when you got that a table that is made up of those values, then you would have been able to draw your graph, right? So you would have been able to draw this graph here, right? Let me show you one of the values. So let's say, for example, v and t, right? So I'm taking t to be 0, right? And you'd have gone t between 0 and 8. So you'd have go 0, 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to find the value of v that would go here. Simply take t equal to 0 and put it in here. So it'll be, so v, right, is going to be equal to 3 times t squared, t. But what is t? T is 0. So you're going to put 0 here. 0 squared plus 4. So we're going to put plus 4. So our value for v will be 0 squared is 0 by 3. 0 by 3 is 0 plus 4. So v is going to be equal to 4. So when t is 0 and you put it here and you work out v, you're going to get v as 4, which is going to be right there. Okay? And then you're going to do the same thing for another point, t equal to 1. Let's say t equal to 1. You're going to work out what v is. Then t equal to 2, you work out what v is and so on. And then you're going to get a series of points that you could plot. So for example, 0, 4 is the first one, right? 1 and whatever this value is the second one, and so on. And you plot it out and you draw your line. You get a nice graph like this. This is called your velocity versus time. But because it's not constant acceleration, in fact, it's variable acceleration, you're going to get a curve as opposed to straight lines. So after you draw that, they want you to estimate the initial speed. Well, the initial speed is right here, 4 meters per second, where you started off, right? And we already calculated it here. For time t equal to 0, which is when you start, the initial speed or velocity is 4 meters per second. So our initial speed will be 4 meters per second right there. The next question was, what is the average acceleration during the last 3 seconds? Well, we come to our rule here. The average acceleration over any particular period of time or any time interval is obtained by finding the gradient of a chord over that interval. So for the last 3 seconds, that'll be t equal to 5, from t equal to 5 to t equal to 8. We'd have to draw this chord and find the gradient. How you find the gradient of any line, or in this case a chord, it will be y2 minus y1 over x2 minus x1. So I'm calling this point here y2, 196, which is this point on the chord, x2, 8, right? And I'm calling this point down here, x1, y1, 579. So to get the gradient of this chord, which is going to give us our average acceleration, right? Average acceleration for the last 3 seconds, y2 minus y1 would be 196 for y2 minus 79 for y1. That goes on top. x2 minus x1 will be 8 for x2 minus 5 for x1. 8 minus 5. And when we divide that down, we are going to get our gradient, which we know is going to give us our average acceleration, and that works out to be 39 meters per second squared. Okay, the next part was to find the acceleration at 3 seconds. How are we going to do that? Well, to get the acceleration at a point in time, this gives us that. The gradient of the tangent at that point in time gives us the actual acceleration. So what we'd have to do is to find the gradient at this time. What is the time they wanted? 3 seconds. So we have to locate 3 seconds, right? Draw the tangent at that point, if they didn't draw it for us, which is a line that touches the curve at that point alone, and then find the gradient of this tangent. That will give us the actual acceleration at that point in time. How do you find the gradient? Well, we have a formula. The formula is y2 minus y1 over x2 minus x1, where x1, y1 is 1 point on the tangent, and x2, y2 is another point on the tangent. So we're going to use this point as x2, y2, and this one here as x1, y1. Okay, good. So y2 minus y1, y2 would be 68, minus y1 would be 0. So it'd be 68 minus 0 on top over x2 minus x1. x2 will be this point here, which will be 5, minus x1, which will be this point here, which is 1.2. So it'll be 5 minus 1.2. When we divide the two, that answer is going to give us our actual acceleration at this point here where t is equal to 3 on the graph. Okay, so with that, we would have completed the syllabus components, right? And in terms of tutorials, right? And we would continue with our revision in the sense that besides this teaching, which is really meant to give you an overall revision of all the topics that we did before, I will continue to do multiple choice and paper 3-2s. So I gave you a paper 3-2 on the WhatsApp chat in the last couple days. I put it up for you. So you can go through that and look at the corrections and see if you're following it, right? My next class, I will go through that paper 3-2 with you. It will, today is Tuesday, so I'll probably do that on either Thursday or Friday. And then on the weekend, I will do another paper 3-2, right? Maybe 2, because paper 3 is coming up before the multiple choice, right? So when we're through with the paper 3-2s, which you could also use to get information for the multiple choice, we will do some more multiple choice papers. So you're always revising up until the exam, okay? So that will bring us to the end of this class for tonight. I hope you guys learned something and revised something tonight. I will see you in the next class. Keep looking at the WhatsApp chat so you will see what I have in store for you. Okay, so God bless, and I'm looking at maybe Tuesday or Friday to do the corrections for that paper 3-2 that I had put up on the WhatsApp chat for you guys. All right, so you guys take care. Good night, everybody.
Good night, sir. Good night.
All right.
Good night, sir. Thanks.
You're welcome. You have a good night.
Bye. Good night, sir.
Same to you.
Bye, Celine.
Bye.
All right, everybody.
Nice, sir.
Good night. Everybody take care. Be careful.